All right, so welcome. This week we are talking about sections 3.2 and 3.3. We're kind of talking about like increasing and decreasing. So yeah, are there any questions about this material? Where would you guys like to start today? Can everybody hear me again? Turn my mic on, yeah. Awesome. Okay. Okay. Maybe there were some things that were like a little less clear as to like how to solve. I especially think that section 3.3, once you like figure out how to solve these, as with a lot of the problems like in this last couple of sections that we've been covering, once you know how to solve one, you pretty much like apply the same process to most of the others. So I guess let's just try to go ahead and do some of that in, let's start with section 3.2. All right, let's start with problem 5 then. Okie dokie. And I am on page 220. And problem 5 looks like this. Okay, so we're verifying that this function satisfies the 3 hypotheses of the Rolle's theorem on the given interval, and the interval is going to be -1 to 3. And then we need to find all numbers C that satisfy the conclusion of Rolle's theorem. So to start with, what is Rolle's theorem? Go ahead and put any one of his like conditions in the chat box. Yes. That is, yeah, that's one way of putting it. Sorry, I'm trying to. My book is throwing a little bit of a fit. I need to get back to the problem. What are the other conditions of Rolle's theorem? Yep. Okay. And the other 2 besides f of a is equal to f of b, continuous and differentiable. Exactly. Okay, so is this continuous? Yes, because it is a polynomial. It is going to be continuous on all real numbers. And differentiable is also a hard yes, exactly. Again, because it's a polynomial, we know it's differentiable and continuous on R. That's just kind of the nature of the function that we're looking at. All right, now we need to verify that f of a is equal to f of b. In this case, a and b are right here. So we're just going to go ahead and plug this in. F of -1 is equal to 2 times 1 squared, which is 1, minus 4 times -1 plus 5. So this is going to be 2 plus 4 plus 5, or 9 plus 2. It's going to be 11. And then f of 3 is going to be 2 times 9, 3 squared, minus 4 times 3 plus 5. This is going to be 18 minus 12 plus 5. And this is going to also be 11. So we've satisfied all of these conditions. We know it's continuous, we know it's differentiable, and we know that f of a is equal to f of b. So then what's my next step? Any suggestions? Yep, I'm going to differentiate it. So I'm going to work with that function right up there. I'm going to say f prime of x is equal to 4x minus 4. And what am I looking to do here? Like, what am I going to do with this? Yep, I'm going to have it equal 0. And sorry, I keep writing my f's differently. I'm going to call this c because that's just like the terminology they use in the book. F prime of c is equal to 0 is the term that we're looking for, and so that is going to be equal to 4c minus 4, and then we're going to solve for c here. So this is going to be 0 is equal to 4c minus 4. Add 4 to both sides. 4 is equal to 4c. C is going to be equal to 1. And what's the last thing I need to check? That's a good thing. I definitely should check to make sure that it exists. Given that we know that f is continuous on all real numbers, that's not so much a concern for right now. I was just referring to making sure it's in this interval. Because we are only looking for c values that are within the interval. Also a good suggestion in the chat box to double check that f prime of 1 is equal to 0. So we could just put that in. So we'd have f prime of 1 is equal to 4 times 1 minus 4. So that's 0, and we're good. But do just make sure that your c is going to be in the interval that you're looking at, so that you're kind of on the right track. Okay, let's do another one of these. Let's just go ahead and do number 7. Here we have f of x is equal to sine x over 2 on the interval pi over 2 and 3 pi over 2. Okay. First things first, we're going to make sure that it's both continuous and differentiable. So this is kind of steps 1 and 2 in one process. We know that sine functions are continuous on real numbers, and we know that sine functions are differentiable. There's no instance where this is going to just not exist. So we can say that yes, this is continuous and differentiable in all real numbers. And that's just kind of a property of the function itself. So now that we know it's continuous and differentiable, then we're going to prove that f of a is equal to f of b. So pi over 2 is equal to sine pi over 4, because this is going to be pi over 2 times 1/2. All right. And what is sine pi over 4? No, I'm calling back to trig. Sine pi over 4. Square root 2 over 2. Exactly. So this is square root 2 over 2. All right. So then we have f of 3 pi over 2, which is equal to sine 3 pi over 2 times 1/2, which will be sine 3 pi over 4. And what is that equal to? Sine, just like a reference kind of to your unit circle, how I kind of think about things is comparing them to the unit circle. I know that this is in the first quadrant, this is going to be in the third quadrant, and usually these, those are kind of like the reflections of one another. If it was in the second or fourth quadrant, what we would end up is a negative square root of 2 over 2, which is not what we want. So those are different numbers. But as Adam says in the chat, it is square root of 2 over 2, and we are good to go. We know that all of Rolle's theorem has been shown. So we're good to go. Okay. Next, we need to show what C is. So we're going to start by taking the derivative, as you guys said earlier. So f prime of x is, what is this going to equal? This derivative. Very close. You're just missing one thing. There's a constant on the inside of this. And that constant is equal to 1/2. So we're going to have to bring that 1/2 to the outside when we're taking that derivative. Does that make sense? This is from, just an earlier section. Okay. So we have our derivative here. We know that we want when f prime of c is equal to 0. So that is when 1/2 cos c over 2 is equal to 0. We're going to simplify this down so that we can get to the nuts and bolts of what's going on here. So that is when 1/2 cos c over 2 is equal to 0, when cos c over 2 is equal to 0, because we know that 1/2 doesn't equal 0. There's no variable there. Alternatively, just multiply both sides by 2. I really hate having c as the variable. I always think it looks like a 1 or something because I never write it correctly. Okay, so when does the cosine of something equal 0? This is how I tend to think through it, because I don't want to take an inverse cosine, because I guess that's just not something that I would think about doing. So when does cos x equal 0? When x is equal to what? Pi over 2. Bingo. To be more specific, it is going to be pi over 2 plus n pi. Pi over 2 plus n pi, right? Yeah. So if we kind of are looking at our circle here, we're going to be on these axes. So pi over 2, and then 3 pi over 2, and then 5 pi over 2, and we're just going to keep going around like that, bouncing. So it's repeatable. Okie dokies. So we're going with when x is equal to pi over 2 plus n pi. So c over 2 has to be equal to x, right? Because we know that we have cos x is equal to 0, and sorry, equal to 0, and we know that cos c over 2 is equal to 0. So x, I don't know what is up with my pad today. Like, what is, okay, sorry, let me readjust my tablet. Okay, maybe this will be better for writing. We know that x is equal to c over 2. We also know that x is equal to pi over 2 plus pi. So now we have it down to the one variable that we want, which is c. I'm going to multiply both sides by 2. And I'm going to end up with c is equal to pi plus 2 n pi. That n, again, is just like to indicate that a lot of these trig functions, just like as they go around the unit circle, kind of repeat on themselves. Okay, that being said, so we have this is our answer. We just need to figure out, we have an infinite number of answers because n can be any integer. Right? So we need to go back up here and compare it to our interval, right? So what is c equal to in our interval? Okay, do you guys understand what I'm doing with this 2n pi term right here? Like what that term is saying? Okay. So let's say we have let's just do like, okay, I'm just putting it there actually when I'm figuring out what x is equal to, because I'm not like solving it like equation wise. So here we have pi over 4, right? And we stated that we had this triangle that was here we have pi over 2, here we have 1 and 1. We had this triangle that looked like this. And we said that this sine of pi over 4 is equal to square root of 2 over 2. We agreed with that. Then we went ahead and we said that was also the case for back here. And this line, which is 3 pi over 4. We said that sine of 3 pi over 4 is equal to square root of 2 over 2. And so the difference between these two is pi over 2, right? Okay, I think I just may have mucked this up a little bit. I'm not sure if this is entirely getting across what I'm trying to say. But the point is that this pi over 2 will just continue repeating. Sine of x is equal to square root of 2 over 2 at x is equal to pi over 4. That's true. Both like that makes this true. If x is equal to pi over 4, then the sine is equal to square root of 2 over 2. And then it is equal to that again when x is equal to 3 pi over 4. I drew 3 pi over 4 in the wrong place. That's not 3 pi over 4. Oh my goodness. I'm sorry. I've had a really long day. Ay, ay, ay. Okay. Oofda. Ignore everything I wrote in the green. That's wrong. I'm wrong. And I'm drawing the triangle badly. Okay. Here's our triangle. This is 3 pi over 4. I was like, why does it look like this? I usually do draw things out when I'm working with trig functions just because I get confused very easily, as you obviously can tell. So here we again have that, and this is a -1 now. And because we're doing opposites, this is still equal to square root of 2 over 2. Okay, so sine x is equal to square root of 2 over 2. Again, that remains true. I just now have my graph drawn correctly where x is equal to pi over 4. X is equal to 3 pi over 4. Then we go around the unit circle once. And instead of pi over 4 and 3 pi over 4, we hit here and we call it 2 pi. Or in this case, it's the 8 pi over 4. And then we go another pi over 4. So this is going to be 9 pi over 4. And so if x is equal to 9 pi over 4, sine x is equal to square root of 2 over 2. What I'm trying to say is that as you just like continue around the unit circle going into infinity, these numbers can get really large, but the function is not going to change. In the chat, we have someone saying, what is n, any number? 2 pi plus n times. Yeah, so n is any integer. So we're going around the circle like an even number of pi times. So in this case, we are looking at this, where we have cos x is equal to 0. 2 pi is 1 trip around, so it's 2 pi times n. Yes, that is the truth if you go 1 trip around. Are you looking at the stuff in the dark blue or the light blue? Oh, the unit circle. Sorry, I just erased that. Yes, 2 pi is 1 trip around. So it's 2 pi times n, yes. So n then can stand for 3. So I'll go 3 times around the unit circle. And I still will end up with like the same y value, even though my x value is much higher now that my n is 3 now. So I am ending up with like plus 6 pi. So what I'm doing here is I'm saying that the cosine is equal to 0 when cosine is equal to 0 when x is equal to pi over 2. And it's also equal to 0 when it's pi over 2 plus pi, which is equal to it's going to be 3 pi over 2, because it's pi over 2 plus 2 pi over 2. Like written explicitly out, it looks like this. And then let's add another pi. And we keep going on and on into infinity, where n is any integer. So the reason I added that on is to be like expressly clear that x doesn't necessarily just equal pi over 2. It equals pi over 2 and all of the next iterations of pi over 2, where the cosine is also equal to 0. Sorry, trig can get really convoluted very, very quickly, I think. And unfortunately, this is not one of my strengths. So, are there any questions about what I just said, or any comments to make it more clear? Okay. So we have one person who is good with it. Good, sweet. Okay. So we understand why that happened. We're keeping that n around as like a placeholder for I'm continuing to go so many times around the unit circle. I'm going to multiply here by 2, and all of it gets multiplied by 2, and I end up with c is equal to pi plus 2n pi. So now the question is, what is n equal to? So that in our interval, which is up here, so that c is in our interval. So some examples of what c is equal to. C is equal to pi. C is equal to pi plus 2 pi, which is 3 pi. C is equal to pi plus 2 times 2 pi, which is 4 pi, which is 5 pi, et cetera, et cetera. C is also equal to pi minus, so 2 times -1, which is negative pi. We just need to find which ones of these, plural or one singular, is in our interval. And the answer to that is pi. So n is equal to 0 and c is equal to pi. So although all of these are true and I need to consider all of these, for the case of this problem in particular, I needed n is equal to 0 so that my c is equal to pi and exists in the interval. Okay. All right. Let's try to do number 11. I'm still on page 20. Check. Yes, I am. So here we're verifying that the function satisfies the hypothesis of the mean value theorem on the given interval, and then find all the numbers c that satisfy the conclusion of the mean value theorem. So basically this is just kind of like plugging in and checking. We have f of x is equal to 2x squared minus 3x plus 1 on the interval 0 to 2. First of all, we just kind of need to go over and ask, is f both continuous and differentiable on this interval? The answer to that is yes, it is. It's a polynomial. then let's go ahead and do f prime of c is equal to f of b minus f of a over b minus a. Okay, so we just need to go ahead and plug some of these numbers in where they belong. Goodness, my pen is so sticky. All right, so first of all, let's take this derivative. What is the derivative of f? Yep, derivative of f is 4x minus 3. Then we also need to find f of b, which is 2, and f of a, which is 0. So f of 2 is equal to 2 times 2 squared, which is 4, minus 3 times 2 plus 1. So that is going to be yes. Oh, no, not quite. This is going to be 2 times 4 minus 6 plus 1. So this is going to be 8 minus 6 is 2, plus 1 is 3. And then this one is going to be 2 times 0 minus 3 times 0 plus 1. So this is going to be plus 1. We have 3 here and 1 here. And then we're going to go ahead and put all of this together. We have f prime of c is equal to, and I'm just going to go ahead and put in here, this is going to be 4c minus 3, and again, I'm substituting c in for x just because that's the notation that the book likes to do. I'm going to end up with f of b, which is f of 2, which I figured out up here is going to be 3, minus f of a, which is 1, over b, 2, minus a, 0. So I'm going to end up with 4c minus 3 is equal to 3 minus 1 over 2 minus 0. I'm going to add 3 to both sides. 4c is equal to 4. C is equal to 1. And then my last kind of check is this in the interval? And yes, it is. Okay. We're kind of pushing up on, we've got 2 sections to go through. We're about halfway done. Do you guys feel comfortable moving to section 3.3? Okay, this I think is the more important of the sections, honestly, at least based on my memory of the class. This is definitely like conceptually very important. We're looking at first derivative test, extreme values, that sort of thing, concavity, inflection points, second derivative tests. All of this is like prime material that they love testing you on. Because this is an online class, I don't think they're going to have you like drawing the graphs, and if they do, I'm not sure how it's going to work. So I guess I haven't really worked with this class in particular before. The other calculus classes I have worked on, they haven't had people drawing graphs. So just like an information for like testing, etc. While it is very important and it's very useful to be able to draw a graph, that's probably not something that they're going to be having you do. All right, so we are on page 228. And we are going to do problem. Let's do problem 211. Okay. So we need to find the intervals on which f is increasing or decreasing. We need to find the local maximum and minimum values, and we need to find the intervals of concavity and the inflection points. So we got a lot of stuff to do with this particular problem. Let's get started. What's the first thing I should do? Yep. Awesome. All right. So I've got my first derivative. Then what? Yep. So I'm going to find out where the first derivative equals 0. And the best way to do this is to, in my opinion, turn it into something that's being multiplied by something. So I have 4x here, and I have x squared minus 1 here. And so this whole shenanigan equals 0 if 4x equals 0, or if x squared minus 1 is equal to 0, slash if x squared is equal to 1. Slash if x is equal to plus or minus 1. Yes, exactly. What we just did there in the language of last week is we found some critical points. Awesome. Okay, so what are we going to do with those? The way that my professor taught me, and that I have kind of preferred to do things since I took calculus, is I draw kind of like a number line. And I mark here is -1, here is 0, and here is 1. And I'm going to kind of use this line to visualize what the function is doing between these points. Yes, so I'm going to find the value of the derivative on either side of the criticals. So I pick a random number. I'm going to pick -2 here. I'm going to pick -1/2 here. I'm going to pick 1/2 here. And I'm going to pick 2 here. All that's important about these numbers is that they're easy for you to think about in your head, and you can easily put back into the derivative. So for me, that's why I chose those numbers. Easy. So if I'm looking at -2, which is below the first critical point, I've got f prime of -2 is equal to 4 times -2 times -2 squared, so 4 minus 1. And so this is going to be -8 times 4 minus 1, which is 3. And it doesn't really matter what the number is. I don't care about the number in particular, because all I care about is the fact that it's to the left, and this is a negative number. So I'm going to put a big old negative sign there. All right, then what about the right of -1? There, I'll be looking at f prime of -1/2. So again, I have 4 times -1/2 here, and then 1/4 minus 1. So here I have 4 times negative a half is negative 2. 1/4 minus 1 is going to be negative 3/4. So what do I have here? I have a negative sign times a negative sign. So my result is going to be positive. And so as I continue, I don't really think exactly about what's going on. I think more specifically about what my signs are doing. So I'm going to kind of do it a little bit more mentally this time. If x is equal to 1/2, I have 4 times 1/2, which is positive, and then I have 1/4 minus 1, which is negative. So positive times a negative is going to be a negative. And then if I'm looking at 2, I have 4 times 2 positive, and then I have 4 minus 1, which is also positive, so positive times a positive. So what I'm looking at here is another way of kind of envisioning this. Sometimes I do negative signs and positive signs. Sometimes I just do like down arrows and up arrows. Because what this is telling me is that if the derivative is negative, then the function is increasing or decreasing. Decreasing, exactly. So okay, so I basically just answered the first chunk of this problem in saying that I know that it's decreasing on what are the intervals specifically that is decreasing on. Yep. And then it's increasing on the other intervals. In this case, it'll be -1 to 0, and 1 to infinity. Okie dokies. Awesome. And also, just a random side note, am I going to be using brackets or parentheses? Yep, parentheses. Sweet. Okay. So that was part A. I'm going to erase some of this so that I have a little bit more room to solve. Whatever the next part is. The next part is find the local maximum and minimum values of f. So, local max and mins. What does that mean? Where do I have local max and mins? I'm not going to go ahead and take the second derivative just yet, because I can do this with the first derivative. Yes. I have my local maxima and minima where I have critical points. So I know based on my critical points that I have a min here, a max here, and a min here. And that's another good thing about the arrows is that I don't have to think, am I moving from negative to positive, and what does that look like? I can just kind of like say, I have a negative slope, I get a positive slope, I got a minimum here. You kind of see the curve. So I have them at my critical points. What I'm going to do actually is I'm just going to put my critical points back into the original function. I'm going to say, what is f of -1? What is f of 0? And what is f of 1? And this will spit out some y values that I can use to define what my local max and mins are. So f of -1 is going to be -1 to the 4th minus 2 times -1 squared plus 3, or 1 minus 2 plus 3. And that is, holy crap, my brain just completely died. That is going to be, what, 2? Okay, so then we get to 0. We have 0 minus 0 plus 3. We've got 3. And here it's going to be essentially the same thing. The signs aren't going to be, well, the signs are just going to be different here. But so here we have points. I have a local max at the point x is equal to 0, y is going to be equal to 3. And then I have a local min at the point x is equal to -1, y is equal to 2, and x is equal to +1, y is equal to 2. So I have 2 local minima, 1 local maxima. What does this tell me about my global min and max? What can you infer about global min and max from this information? That's the correct answer. The answer is nothing, really. The absolute / global maxima and minima are like a completely different process. We don't have an interval, notably, to work with, so we can't take the edges of the interval and compare them to the local minima and maxima. You guys have done that, right? I'm not jumping ahead. We did this last week, I think. I'm pretty sure. I might have just asked a really stupid question. Yeah, okay, sweet. So we don't need to take the edges of the interval because there is no interval. We have these local maxima and local minima. We can kind of take a look. Actually, does anyone kind of know what the shape of an x to the 4th function is? Generally speaking, without any of the coefficients and additions, an x to the 4th function kind of looks like this. So we can kind of assume that it's going, both ends are going up to infinity, but I'm not entirely sure how having that extra x squared in there is going to change things around, so I want to go ahead and say for certain that our global min is 2. But we know nothing about the global min and max. We only know things about the local, and that's fine. That's all the question asks about. Just don't go inferring things that are a little beyond what we've got right now. Okay, so the last question is concavity and inflection points. So where am I going to start with this? Yes, we're going to take the second derivative. So the second derivative, let me pick a color that I haven't ruined yet or not been used. So f double prime of x is going to be equal to 12x squared minus 4. Right? Yeah. 12x squared minus 4. And then I'm going to set this equal to 0, just kind of like I did before. So that is going to be f double prime of x is equal to 0 is equal to 12x squared minus 4. And I am going to say that I'm just going to divide out of 4 between all of these. It's 0 over 4 is going to be 0. But I like having things a little simpler. So 0 is equal to 3x squared minus 1. And that is equal to 0. So we're solving for x. This is going to be 1 is equal to 3x squared divided by 3. So x squared is equal to 1 over 3. So I'm going to take a square root. X is equal to and because math dislikes having square roots on the bottom, this is also plus or minus. Right. This is going to turn into plus or minus square root 3 over 3. So, what is this? What did I just do? What did I just find? Yes, these are like the same type of critical points. I wouldn't call them critical points so that I don't get mixed up with what I did up here. It's unfortunate that I chose to do this in the same color. So these are critical points from the first derivative. I would just go ahead and call these inflection points. And what do we know at inflection points? We know that the concavity is going to be changing at inflection points. Very similar to how we knew that the before and after critical points, the direction of the graph would be changing from increasing to decreasing. At inflection points, we have the concavity switching up. So we're going to do the exact same thing we did before with the line, because I really like the line thing. It just is a really good way for me to visualize that. I don't know if, did your professors use the same sort of thing? In some of my other calc classes, they didn't, and I was like, okay, I don't like that, but okay. Easy point in between these is 0. And then I don't really want to think too hard right now, so I'm just going to go with like 10, negative 10, and 10. Because why the hell not? Then I'm going to be using my second derivative instead. So this is going to be f double prime of negative 10, f double prime of 0, and f double prime of 10. All that matters is that it's like to the left or to the right of something. And we established that f double prime of x is equal to, oh wait, I have it written right there, is going to be 12 times 10 squared, which is 100, minus 4. So that's going to be very positive. And it's going to be the same thing right here, so 12 times 100 minus 4, very positive. And then I have 0, which is going to be 0 minus 4, which is negative. So what am I looking at here? Shoot. Where am I concave up? Where am I concave down? Come on. Sorry, Zoom has been giving me a little bit of trouble today. So when f double prime is okay, when it's positive, we're looking at concave up, right? So we're going to say from so it's positive in two places. It's going to be positive from negative infinity to square root of 3 over 3. And it's going to be positive square root of 3 over 3 to infinity, right? And then it's concave down between the two of them. Okay. I don't think there's any part of the problem that is not answered on this kind of whole kind of experience. Are there any questions about what happened here? Oh, yeah, for sure. How would you find that? Yep, we just plug it into the original function. So the comment for those who are listening later, because I know you can't see the chat box, sometimes you need inflection points in the form x comma y. The way you would do that is you would say, I have my x, which is minus square root of 3 over 3, and then I would just go ahead and put that in my original function. And then I would do that again. I would have another inflection point at the positive version of that. So yeah. All right. Let's try another problem. I'm gonna clear this drawing. Let's just kind of do another like whole type process, or let's do problem 30 actually. Do you guys all have your books with you? If not, I can kind of sketch it out. This is a good kind of visual. Okay. I'm just going to do a quick sketch. It's not going to be perfect, but it is going to work. Okay. So we are asked, using this graph, to find which points have certain characteristics that are the case. We are looking for where they're both positive, the derivative and the second derivative. Where they're both negative. And then we're also looking for a place where dy dx is negative and d squared y dx squared is positive. So first things first, my gut reaction would be to sort these points into where is the first derivative positive and where is it negative, because that's the thing that's really easy to see right here, right off the bat. So which points have a positive derivative? B and C, yep. Which ones have a negative derivative? A and E. And as a side note, D dy dx is equal to 0. Exactly, you guys got this. Okay, what about the second derivative? How can I like look at a graph and figure out what's going on with that? Exactly, concavity. So if I have a positive second derivative, what kind of concavity am I looking for? Concave down or concave up? Up. So you notice that I abbreviate that as CC up. That's just my way of writing it quickly. Yes, the curve is above the tangent. That is an excellent, actually, way of viewing it. So what points have a positive second derivative? Where is this graph concave up? A and B. Yep, right here. As Adam said, the tangent lines, I'm just kind of sketching some tangent lines, and all of them are below the graph. The curve is above the tangent line. So I have concave up right here, A and B. Now, where do I have negative second derivative? This is probably an easy question. Yep. Yes. C, D, and E. D does count here because a critical point does not necessarily mean it's an inflection point. If you remember to problem 11 we did, we had critical points at -1, 0, and 1, and inflection points at completely different numbers, and that's where the things were equal to 0. So at D, it is totally fair game for this to be concave down. So yeah, and this graph gives no indication that it is it could be like a repeating periodic thing, and E might be some sort of inflection point, but we don't have the information to do that, so we can't extrapolate that it is. So we're going to say that E is concave down. Okay, so now that we have all of this information, we can just put it together. Where are they both positive? Well, the first derivative is positive at B, and the second derivative is also positive at B. So I'm going to say B is where they're both positive. Where are they both negative? Here I'm looking at A and E. A is positive, so not going to be that one. E is negative. So yep. And what about this last one where it is negative and the second derivative is positive? Yep. Point A. What does the profile for C look like? It's just going to be the inverse of this. So where dy dx is positive, d squared y dx squared is negative. An example of that, which is not like asked by the problem, but we can see it's going to be easy. Okie dokies. So working with graphs is good, just to like become more familiar with them and be more comfortable working with them. Does anyone have any questions about the material? Shoot. Sweet. In that case, I'm probably going to let y'all go. So yeah, if you guys do have any questions, of course, feel free to email me, and I'll either get back to you or include your questions in the next week video. Just like make it a priority to get those done first next week. And if you don't have any extra questions, have a wonderful week, and I hope your quiz goes well.